LINFO1131. Je vais donner ce cours en anglais, mais vous pouvez parler français, c'est pas un problème. It's French friendly, but if you're an English speaker, it'll be fine. This course is a successor course to the second year course 1104, and we're going to do things that are much more advanced, and you will see that. First, before I continue, I want just to make a few seconds of respect for the people in Ukraine who are fighting for their freedom and for our freedom in Europe. Okay, thank you. So, I will first explain how the course is organized, what we're going to do, how you can get maximum points and everything. Sure, that's interesting. And then I will give today a refresher of the previous course. Very fast. All the things we saw that are important in the previous course, I will compress them into today's course. And so I assume that you know that part very well, that you have perfect memory of this previous course, because I'm going to go forward after that. Okay? The course is organized as follows. There's a weekly lecture. Today is the first one. And I strongly recommend you attend because usually I give you lots of intuition and examples and things. Okay? There's also a weekly lab. Not the first week. I will send messages for that. It depends on how many people are enrolled. Probably we will have 2 lab sessions at different times. Okay, and we will mark your attendance, and if you attend all the labs, you will get a 1-point bonus on the final exam, which means that it is technically possible for you to get 21 points out of 20. Of course, we will round it down to 20 if you do that. So that is something to encourage you to come to the lab sessions. And there's another advantage coming to the lab sessions is that the simple fact of being there and trying to solve the exercises will automatically improve your points on the exam. So it's a double benefit coming to the lab sessions. Okay? And there is a Moodle for the course, and everything will go on the Moodle, so if you're not yet enrolled on the Moodle, please enroll yourself very fast. And for the grading, there's going to be a midterm. This one is optional. You don't have to do it. It'll be around week 7, the smart week, but we can change a little depending on whether you have other kinds of deadlines, so just to make sure there's no conflict. And this will correspond to 5 points on the exam. There's also a project. This will be a practical project where you implement something. This one is mandatory. You must do it. Well, if you don't do it, you will not get the 5 points. So the project is also worth 5 points on the final grade. And this one has to be done in groups of 2 students. And in case you can't find a second student, you can do it alone, but never in groups of 3. Always 1 or 2. Okay? And the final exam will be on 15 points. 5 points corresponds to the midterm, so basically I will take the maximum of both. Okay? So if you do very well on the midterm, then you can consider yourself to be dispensed for part of the exam. And the rest of the exam is on 10 points. Okay? So if you do very well on the midterm and the project, and if you attend the labs, you can already succeed the course without coming to the final exam. Okay? So I like this approach. Students like this approach because it de-stresses the exam, encourages you to work during the year. So my goal for this course is that you learn the stuff. And I don't care how you learn it, as long as you learn it. So this seems to be a good approach to encourage people to learn the stuff in the course. Okay, so that's how we organize it. So anything that changes, any kind of things, announcements, it's all in the Moodle. And I still have to organize the lab sessions, the times exactly, because it depends on how many people are enrolled. So I didn't really know exactly how many people. So now we will know that this week. So the first lab sessions will start next week, okay? And I will send message on the Moodle for that. Okay, we will use 2 software systems. So the Mozart system with the Oz language, this you know, but we'll also do perhaps some lab sessions on the Erlang language and system, Erlang OTP, version 25. And so this one is available from erlang.org. So you will see that later in the course. This is a very good language for building large, robust software systems. It's one of the best languages for that. And it's an industrial language. Many companies use this language, especially game companies. So if any of you has played Call of Duty, I don't know if you know this game, Call of Duty, then you have also already run Erlang, okay? So this is, I think, a very good language to learn for this course. Okay, so let me talk about the content now. So I'll first give you kind of an overview of what we see in this course. So it's kind of a futuristic, advanced course. I want to prepare you for what's going to happen in the next 10 years in programming. So even if today not all the ideas are being used, they will be used for sure. I know this for sure because I have a very good crystal ball. And so this is what I'm going to teach. So there are 3 main themes in this course. The first theme is concurrent programming. Concurrent programming is supposed to be very hard. You saw already a little bit of it in the previous course, 1104, on deterministic data flow, which is a very nice form of concurrency. So we'll continue that. We'll see many forms of concurrent programming in this course. It's actually the official name of this course. It's about concurrent programming. So this is kind of the main theme that runs throughout the course. And I want to make it easy. It's considered very hard. The most general form of concurrency is very hard. If you've taken a course from Charlotte Becher, you can see that it's actually quite hard. But I want to help you make it easy. So I'm going to kind of cheat by showing you paradigms where concurrency is very easy, okay? And not just deterministic data flow, but other kinds of paradigms. So that's the first theme. The second theme is a very futuristic theme, which is declarative programming. This is the easiest by far way to program. And people are understanding this more and more tools like a cloud are using these techniques. So I want to show you really the power. So it's going to be like half of the course. We're really going to see the power of this approach. That's the second theme. And the third theme is non-declarative. So you can't always use declarative, unfortunately. So you cannot always avoid non-declarative. But still, you can make it easier. So you can see that kind of the theme is how to make programming easy as possible, okay? Using the right concepts and the right abstractions, okay? And in a more kind of diagram, there's actually 2 main parts in the course. Declarative, that's the red box, and the black box, non-declarative. And declarative, we will see 4 paradigms. So there's sequential, functional, deterministic data flow, but also lazy evaluation and lazy deterministic data flow. And these are very powerful paradigms. It lets you write algorithms in a very powerful way that are completely declarative. And I'll explain exactly. This gives you many advantages. It's very easy to write, to testing is very easy. Maintaining is very easy. So you want to do it all the time, actually, the top one. But you can't do it all the time. There are limitations, which we will explain. And the limitations have to do with non-determinism, which I already mentioned in the previous course. So we're really going to see how to attack non-determinism in this course, okay? And there's different forms of concurrent programming based using nondeterminism, message passing, and shared state. And this is really where we're going to see multi-agent and Erlang. So Erlang is the kind of the best system for building large, fault-tolerant concurrent programs. See, the problem is not just concurrency, it's failure. It's that things can crash, especially in a big system, things can crash. So this makes the things especially hard, okay? But if you do it the right way, you can make it easy. So we're going to see Erlang, which actually pioneered this, and very large systems that crash and have to keep running forever are written in Erlang, okay? So there's many examples of this. One example I know is in Denmark, so the country of Denmark, the National Health Database of Denmark. So all of the citizens, the doctors, the hospitals, the pharmacies are all connected to this database, and this database has to be always running. It never can crash because people can get sick anytime, okay? And this database is written in Erlang, okay? And it's running in Erlang and it never crashes. So that's a very strong property, and we're going to see some of that in this course, okay? So this will help you a lot. That's also very important for gaming. It's less important for survival of the games, but in gaming, whenever the game is not running, you have a large multiplayer game, then people are unhappy and the company is not making money and so on. So they want to keep the game always running, okay? And that's why also a lot of infrastructure for games behind the scenes is written in Erlang as well, so that it's always running and never crashes, okay? So this also we're going to see in this course, how to write software that never crashes. And you can update it, you can debug it, and it never goes down. That's pretty strong property, okay? So that gives you kind of the themes of this course. You see, we're going to go much farther than what we saw in the previous course. We're going to kind of push it to the limit. And here's sort of an approximate schedule. Probably we will sort of be respecting this. It depends on how fast we go. Since this is kind of a new course, so the speed is not completely fixed yet. So the first week, S1 is today, is the refresher. And then we will have 2, 3, 4, and 5 on advanced declarative programming. And then we will have 6, 8, 9, 10, 11, 12, 13, 14 on non-declarative programming. Probably the midterm will be week 7, but this could be sometime different. It's around the middle of the course. Okay? So next week, for example, we're going to talk about lazy evaluation, which is an advanced form of declarative programming where programs only run when you need the results. So this is a very interesting way of programming. And then we'll see how to build algorithms that are declarative and very efficient, advanced declarative algorithms. And finally, we see the limits into week 5. You can't do everything, and there's actually a strong barrier, things you can do, things you cannot do. We're going to see that. So you're going to understand that very well in this course. Okay? Okay, very good. So that's the schedule. These slides are very new, so I will put them on the Moodle after the course. Okay, you will find them on the Moodle. And today I want to give a refresher of the previous course. So I'm going to go very fast and give you the concepts we saw in the previous course. Okay? These main concepts are needed for 1131, and normally I taught them in the previous course, but if you forgot completely the previous course, then you just have to pay good attention today, and maybe things can come back, okay? And you can look it up. So if something is not clear, you have to look it up in the previous course. So starting with the next week lecture, I assume that everything I say today is perfectly understood, okay? This is something normally you saw. Today's refresher. It's important to give refresher because I know that people forget things, okay? And it's good to remember sometimes. One of the first things we saw in the previous course was functional programming. We saw that functional programming is the foundation of everything, okay? And especially higher order, which I will explain, where functions are first-class data. It's all data abstractions, and all languages are built using that. And in the previous course, we saw the lambda calculus. Remember that? Well, we're not going to see the lambda calculus anymore in this course, because this is more of a practical, not so much theory course. But the lambda calculus is the foundation, okay, of all the programming. And functional programming is the best paradigm for testing, maintenance, and proving that your program is correct. And that's important for complicated programs. And it's more and more being used in all different forms. So the main example is all the cloud analytic tools, which started from Google and started from MapReduce. And if you go into the course on cloud computing, you will learn that. So I will not see cloud tools here, but I recommend you take the course on cloud computing, and you will see them in these tools, and you will see that they are very functional, okay? And they're getting more and more functional. And so in this course, we're going to push this as far as we can, this functional idea. We're going to push it for concurrency, and we're going to push it for algorithms and efficiency, okay? Because it's so good, we want to use it as much as we can. Okay, so that's what we saw previous course. Remember this, remember invariance. Invariance is basically loops. Remember how whenever you do a loop, and Taylor recursion, remember Taylor recursion is a loop, is a while loop. So loops are very important, of course, because you always want to do computations repetitively on a whole bunch of data. And I will give you a simple example just to refresh it. So here's an invariant. N factorial is equal to I factorial times A. So do you remember how this works? You want to calculate N factorial. So N is constant. It's like the input. But I and A are varying. They're not constant. They can be different values. So this invariant is a formula that's always true, and I and A will be having different values. And you start by I will be equal to N, and A will be equal to 1. Remember that? If you do that, then the formula is trivially correct. If I have N factorial equal N factorial times 1, okay? Remember how it works? And this one. Okay. Okay, so let me continue. So, and whenever you do a loop, invariants are the thing that you have to do. And you can see how it works, huh? Remember how it works? I actually call this principle of communicating vases. If I have two bottles with a pipe, one goes down, the other one goes up. So the input argument I will decrease, and this forces the other one to increase, and that way you can compute the result. So whenever I goes down by 1, A will go up in order to keep the invariant true. So the motor is that the invariant is always true. Okay? This is something that we will use when we do complicated loops. So you have to make sure you understand this. Okay? So here's just code for this function in C and in R. So C is very similar to Java. So int n, you have A and I, and then you have a while loop, and while loop is increasing A and decreasing I here, and the invariant stays true at the beginning of each loop iteration. Okay? Sorry, this has to be 10. Factorial of 10. Here is the OS code, which is a recursive function. A and I are the arguments. So here they are loop variables. Here they are arguments. And whenever I do a recursive call, it will be I times A and I minus 1 until I becomes 0. Okay? And so these two programs are computing the same thing and with the same efficiency. Okay, you see that? See how it works? Okay. Okay, so that's something we saw in the previous course. Okay, another thing we saw was higher order programming. This is something also very important. It's the foundation of many things. Okay, so here's an example. So a function is just a value. It's like a number or anything, a value stored in memory. And you can pass it as input to another function or get it as output. Okay? And we use this for building data abstraction. And here's a simple example we saw. The function add n returns another function, which is an anonymous function. Remember the syntax with the dollar, it means it's an anonymous function. It's just a value. And this function has one argument x and returns x plus n. Okay? And if I say add 5 is equal to add n of 5, then add 5 is a function of one argument that will add 5 to its argument, and add 10 is a function of one argument that will add 10. Now remember we saw the concept of the order of a function. Okay? The order, every higher order function has an order. Remember that? So what's the order of add n? You still remember that? Anybody can tell me? What's the order of add n? Oh, it's very complicated. What's the order? 2. Yes, very good. The order of add n is 2 because the output is a function of order 1. So the order, a function has order 1 if all the inputs and the output are not functions. Then it's first order. And otherwise it has order n plus 1 if there's at least one function of order n in the inputs or the output. So the output here is a function that does x plus n. So that function is first order because x and x plus n are numbers. So add n returns a first order function, so it's second order. Okay? So remember we saw that done. And how does this work? What is the magic that makes this work? So add 5 and add 10 are different. These are two different functions. How does it work? It works because of closures. And closures are also called lexically scoped closures. I also call them procedure values because in the kernel language we have procedures. In French they're called fermeture. It's closed, fermé, because it packages an environment. Okay? And so what's stored in memory is two things. So A1 would be the value of add 5, and A2 is the variable which has the value of add 10. So for example, A2 has the procedure code. So this is symbolic, but in a real implementation, this would actually be a pointer to the code of the function. And then it has an environment which maps this identifier n to some variable. So each procedure has its own little environment. And it's a closure because it's like a package. It's closing over the environment at the definition. So this is called a closure. And all programming languages use this. This is one of the main inventions of programming languages, closures. With this, higher order programming really works very well, and you can build abstractions with it. Okay, so you have to remember this concept of closures. It's a fundamental concept. Okay? So that's how the add-end works. Here's another higher order example. This time, the function is an argument and not a result. Okay? The function map will take a list L, and I'll talk about lists later, but here I'm already using a list, and it will apply the function f to every argument of the list. Okay? And this function is tail recursive. So remember I talked about invariants and loops, and tail recursion means that the recursive call is the last call. So how does that work? This is something special that works because we have single assignment variables in our model. This function is tail recursive. The last call in the body is map. Here you can see it's building a list. FH is a value, the bar is a list pair, a const cell, and map is a recursive call. So it looks like the list is being built after the map, but this is not true. This is actually tail recursive, and this is very important. So I will explain how that works to refresh your memory. So here is the final call of the map. So how does this run? This runs, I will translate to the kernel language, which is the basic primitive language that gives you the semantics. Okay? So the way this runs is that map is actually a procedure with one extra argument, which is the output. So I will not write everything, but I will show you how this call is translated. So the way this is translated is that the map call is actually at the end. And the way it works is that I have R, which is the result, is going to be so here I have a function f returning a value, and I have map. So this function returns some value, which let me call it h2. So I have h2 is equal to fh here. And then I build the result. R is equal to, so R is the result here, is equal to h2 followed by the next piece. Okay, so R1 is another unbound variable. So I'm building the result. R is the result. I'm adding h2 to the result, and R1 is an unbound variable that's being passed to the recursive call. And so this means that the recursive call can be put at the end. It has to be put at the end. It's tail recursive. This is crucially important. It's important for concurrency, as we will see later. It means that we can build concurrent agents that are functional. And this is extremely important for pushing declarative programming as far as we can. Okay? So this map function is tail recursive because of unbound variables, because we can build the result with an unbound variable like a whole, here, R1, and pass it to map. And it is this recursive call to map that will fill in or bind R1. Okay? So the fact of having unbound variables means that list functions are tail recursive, and this will allow us to make concurrent functions, deterministic data flow. Okay, so this is the first example of that. Okay? More abilities of higher order. I'm not going to say more today. We saw many abilities of higher order. Genericity, instantiation. So genericity is where the function is an input. Instantiation is where the function is an output. Function composition, where you compose functions. Abstracting an accumulator. This is the fold operation, which I'll show in a few minutes. Also encapsulation. We can hide things inside. We can also do delayed execution. You can take any statement and turn it into a zero argument procedure, and that's a value, and then pass it somewhere else, and it will be executed somewhere else. So this is like a delayed execution. It means you can build constructs like while or if or repeat statements, any kind of a statement. You can build it using higher order. So you can see higher order is really a foundational, very important thing. And this was invented in the 1960s, and it changed everything for programming languages. Okay? All the languages that were before that were actually broken. Lisp and Fortran, for example, which were invented before this, were broken and had to be fixed. Whereas all the languages that were invented after that were good, were not broken. Okay? So this was like the major invention for programming. Okay, so this is what we saw. So you have to remember that. We're going to use it all the time in this course. Okay? Another thing we saw in the previous course was symbolic programming. Programming not just with numbers, but with abstract kind of structures. And we saw things like trees. Remember the tree algorithms? We saw records. And we saw lists. So here is a grammar definition of a list. So the list L is either nil, the constant nil, or, so the vertical bar means or in grammar notation. An element E followed by a vertical bar. So the vertical bar with quotes is a vertical bar in the definition, in the thing we're defining. So notice the two uses of the vertical bar. They're different. So a list is a recursive data structure because it's defined in terms of itself. And any recursive list function, like map, will follow the recursive grammar definition. Okay? So lists are ubiquitous. All languages somehow use lists. Some of them it's kind of hidden. Some of them it's very explicit. Like in languages like Scheme or Erlang or Haskell, they will be using lists explicitly. And in ours, you have many syntaxes. So there's what we call syntactic sugar for lists, since they're so ubiquitous. Okay, and then one important concept that's used is called pattern matching. This is used in all symbolic languages, and it really makes the programs easy to understand because we kind of use pictures. In the left here we have a list, 1, 2, 3, nil. I show it in a tree notation, okay? It kind of like a directed graph. This corresponds to the syntax. And on the right, I show a pattern, which has the same syntax and has identifiers, H and T. And pattern matching will make those two correspond to each other. And in Oz, it's called the case. But different languages will have different names for this. If you write programs in Scala, for example, you will also have pattern matching. Okay? So it matches the actual list with the pattern, and H will be bound to 1, and T will be bound to the list 2, 3, nil. And patterns can either match or they don't match, they fail. Okay? So pattern matching is something we're going to use a lot. Okay? And let me show you another higher order operation on lists. This is a very important operation called fold. It's just a function that we call fold. But somehow this function, this particular one, is very important. So I refresh your memory on this. And there's many reasons why it's important. It abstracts an accumulator. So in the invariant, remember the I and the A? The A is called an accumulator because you build the result. You accumulate the result. Okay? And the fold operation hides the accumulator inside, so you don't see it when you call fold. Okay? When I have a list L, which is A0, A1 up to AN minus 1, I have a function that take F, which is a binary operation, like summing, making the sum, okay? I can define the function where I start with some beginning value, U, and then I do UFA plus A0, and then plus A1, and I do plus AN minus 1, so I'm summing all the elements. So the fold kind of collapses all the elements of the list into a single result. Okay? So it has three arguments: the list L, the binary function F, and the beginning value, which is U. Okay? And S is the kind of folded result. Fold is also called reduce. So another name for this function is reduce. And if you see in the cloud analytics, there's a function called map reduce. The reduce is just a fold. Okay? So fold is a very important higher order function. Another reason why it's important is that it is the heart of a concurrent agent. Actually, the fold can model the state transition of a running concurrent agent. So you see, this is kind of an essential higher order function. Okay? So here's one way you can define it. I call it fold L because it's left associative. There's another version called fold R, which is right associative. Okay? This is the left associative one, LFU, and whenever it recurses down, it replaces U by F of U and H, which is the element. Okay? And it recurses down all the elements of the list, and so reduces everything to a single result. So U is an accumulator here, like the A. And we can use fold L to do many things. Computing the sum of elements of a list is just one line of code. So is fold a tail recursive function? What do you think? Is it tail recursive? Yes or no? You tell me. Is fold tail recursive? You should know this. It's very easy. You just have to look at the code. Yes?
Yes.
Yes, it is, huh? Because the last call is fold. The F call is done before. So fold is not building a list, huh? It's not like map, where you're building a list. Here I'm collapsing. I'm compressing all the results, all the elements of the list into one number, or one thing. So the fold is definitely tail recursive, and you can use fold as the heart of a concurrent agent. So the list, in that case, is a stream of messages being sent to the agent. Okay? List functions you can actually turn them into concurrent agents. So there's actually a strong connection between functional programming and concurrent data flow programming. The list functions, which are just functions, you can use them as concurrent agents. And fold is like the most general one because you can use it for any agent which has an internal state. So the U is like the internal state, and the H is a message that you send to the agent, and it transforms, and F is the internal implementation of the agent, the state transition. So you can see that whenever the message H arrives, it transforms the the internal state U into a new internal state, F of UH. So you can use fold to build a concurrent agent, okay? So you can see fold is actually one of the key higher order functions, okay? The key function. Okay, so let's go on now. So I'm still refreshing you here, huh? This is all old stuff, huh? So let's talk a little bit about data abstraction. In this course, we're going to go farther. We saw already some basic principles of data abstraction in the previous course. Okay? So a data abstraction is taking a piece of the program and making a box around it, encapsulating it, and it can only be accessed through the boundary, which is the interface, and this interface obeys some rules. You can only call it in a certain way. If you try to call it in a different way, you get an error. It doesn't work. Okay? And so this protects the inside of the box. So it protects the inside. So it has three advantages. One is that since the inside is protected, you know that you're guaranteed you're going to use it in the right way. So it will work correctly. You can't really break it by calling it in weird ways. Okay? So it's a guarantee that it will work. Also, reduction of complexity. When I call the abstraction, I don't have to know the implementation. I don't have to even see that code. Okay? I just have to know the interface, which is very small. This is a key concept, not just in programming, but in the whole of society. When I drive a car, I'm only using the interface of the car, and I don't know how the motor works, okay? Actually, I a little bit know, because when I talk to the mechanic, it's good to know a little bit. But I don't have to know all the details of how the car works, or how a computer works, or how a television works, or a mobile phone, okay? So it makes my life easier. It reduces complexity. And the consequence of this is I can build very large programs, much larger than a single human. And it's all because of data abstraction, okay? I can build millions of lines of code, 10, 100 million lines. Engineers can work for 20 years building libraries. And no single person understands that, okay? Each person understands their own piece, but the other people will see only the interfaces. This is a key concept. If you didn't have this, you could not organize society. In fact, if you're a philosopher or a sociologist, you also understand this, because human organizations also use this idea. Okay? But in a programming language, this is essential, that this data abstraction. And notice it's built on top of higher order, which is using closures. So you can see closures are like the foundation for this whole construction. This, you can see, was a very important invention. Before closures, people were kind of clueless. After that, we could start building large systems. Things really accelerated with closures. Okay. So there's two concepts defining data abstraction. So the lexical scoping, where an identifier can only be seen in a part of the program, which is called the scope. Remember the scope? One identifier, it's the part of the program where the identifier refers to the same definition. It's a question I love to ask on exam, and people don't always get it, okay? So scope is very important, and then higher order. Because higher order lets you build these interfaces, because it has the closure inside the functions, okay, hidden. And so that's how you build them. And there's somehow, it's very interesting, there's actually two kinds of data abstractions. Objects and abstract data types. They're fundamentally different things, different. And both of them have a meaning. So this you can see if you do a mathematical definition, okay? But you can see the intuition. So an object, everything is inside the object. And an abstract data type, you have two things. the values and the operations. So an automobile is an object, but a vending machine that takes it where you can get a can of Coca-Cola with a coin is an abstract data type. Because you have the coins, you have the cans, which are the values, and the operation, which is the machine. These are separate things. Whereas in automobile, there's only one thing, which is the automobile. Okay? So there's two kinds of abstract data abstractions. And we saw how it's done in the previous course. This is the stack. So this is recalling stuff we saw in the previous course. So do you remember how this works? So we have a new stack operation. We have push and pop and is empty. And the way it works is that you take the value of the stack and you encapsulate it inside a kind of a box, a safe deposit box with a key. Okay, so wrap and unwrap are like doing cryptography. They're hiding the data, and they have a shared key. So inside of wrap and unwrap, there's a shared key. So we didn't see all the details of how it works, but we will see that we will investigate this more in this course. Okay, because this is a very important concept, and it's using some kind of a cryptography. And if you see how the push function works, W is like a hidden stack. It's a value, but you cannot look inside. An unwrapped W returns the stack, and then you build the new stack, which is X bar S, and then you call wrap to package it up again, to lock it up inside the box. That means outside of this code, nobody can see. It's hidden. Okay? Okay? And wrap and unwrap are important, of course, and they're hidden from the rest of the program because of static lexical scoping. Okay? So this is how you would do an abstract data type. This is kind of like the semantics of it. Huh? But the same stack, you can define it as an object. It's very different now. Very different. The same stack, but now you don't have stack values and push and pop. Now everything is together. The object itself knows the stack value and the operations. And the way we do it here is by using a cell, which is a variable we can update. Okay? So the object is like a one-argument procedure, and the argument is the message to the object, M, and if it's a push X message, we call push. If it's pop X, we call pop, and so on. So there's a case statement there that will choose the method. So those three procedures are the methods. And the case statement chooses the method, and that's called procedure dispatching. This is all object-oriented terminology, okay? And the cell is hidden with static scope. So the same stack as before is now an object and not an abstract data type, okay? So there are two different ways of doing things. So this is what we saw before, but it's important to really understand. And objects are very important. So usually languages, they give special syntax. This code here is like the definition of an object. You could actually see this as the semantic definition, because we have seen the semantics of all this. Remember the semantics we saw in the previous course? Well, in this course, we won't see so much semantics anymore. This is not so theoretical course, but we did see the semantics of these procedures. So this is, you can consider this code to give the semantics of an object. This is completely defined mathematically, okay? And usually languages, they don't do like that. They define their own syntax. So Oz has its own weird syntax for objects. This is an example. But many languages have their syntax. Java is an object-oriented language which has its own syntax for classes and so on. Oz has its own weird syntax also for objects. And it's internally, it's doing like this. but the programmer will use this syntax, okay? So the syntax is actually nice to have a syntax because it guarantees that you cannot do things in the wrong way. It guarantees that the object is defined in the right way. It's also more readable, because the object concepts, you see the methods directly, okay, the attributes. Okay, so that is the kind of data abstraction you saw in the previous course. In this course, we will go farther than that. We will study more how you use data abstractions and also how you combine them with other kinds of things. Okay, so this we saw in the previous course. Now I want to talk about concurrency, but I will first make a small break. So we will make a small break, and then I will refresh your memory on concurrent programming. After the break, I want to talk about deterministic dataflow concurrency. This is also something we saw in the previous course, and we saw a very simple form of concurrency called deterministic dataflow. But in this course, we're going to see many, many forms of concurrency, and this is only the first one, the simplest one. In a concurrent program, you have multiple activities that are executing simultaneously, and they're independent of each other. So it's like more than one program is running at the same time, but inside your program, okay? And in order to implement that, we add a new language operation called thread-end to create a new concurrent activity. So this concurrent activity is called a thread, okay? And we saw that, in fact, in a computer system, there's different levels of concurrent activity. Yeah? The thread is the most basic one, but maybe I just give you a refresher. So you have threads. Threads are sharing the memory. But you have a higher level of concurrency, which is called a process. Each process has independent memory space. So this is what's happening on a single computer. And the next higher level is a compute node or a computer, where you have separate hardware. The thread is the most basic form of concurrency because all the threads are sharing the memory, whereas in an operating system of a computer, you will give each process an independent memory space, and of course they're still running on the same computer, and the next level is where you have actually separate hardware. You can use similar techniques for all of these, okay? If you look at these, if you have independent memories, this is called a distributed system because the memory is independent, and the only way to communicate is by sending messages because the memory is independent. So if I have two computers on the internet, they will be sending messages to each other. There's another course that does this called LINFO1131 which studies distributed systems. So we're not going to study that here, but this is actually very interesting because these processes are completely independent. They can even fail independently or crash. A compute node can crash even if the other nodes are still running, okay? So this makes things even harder. Whereas in a threads, normally they will be inside one process and they will share data. So it's not possible for one thread to crash and the others keep running. They will all keep running, okay? So this is what we saw in the last course, the thread concurrency, and we saw it inside of functional programming. So we have functions and unbound variables. And the way that two threads talk to each other is because they share a variable. Both threads know the same variable, and they will either bind or read the variable. Okay? One thread binds, one thread reads. So here's a simple program. The first thread will do x equal 1, and the second thread will do y is equal to x plus 10, and then it displays y and browse y. So this program always displays 11. Now, it can execute in many different ways. Okay? This is specific concurrency. That means we don't know when these threads are going to run. Okay? We don't know. Maybe the second thread will run first, and it will fall asleep after a certain piece, and then the first one will run, because you have a piece of the program called the scheduler. Because the threads are independent, they're not connected to each other. They're separate programs. Okay? So you really have to understand that threads are independent. But still, this program will always display 11, even if the threads are running in a different order. That's very important. Yeah? This program, even though the threads are running in different order, it will always display the same result. And this is a very important property of deterministic data flow. So here I make a diagram. I call them activities. This is like the thread. So there's on top you have the thread doing y is equals to x plus 10, and then later on, so the time goes from left to right, it does browse. At the bottom you have the second activity. So there are two independent activities. So let's say the first one is running first. It does y is equal to x plus 10. But x is still unbound at that point. So what's going to happen? What does the plus do? This is where we have data flow behavior. So data flow is a very important concept. It was actually invented in the 1960s, okay? Many things were invented in the 60s. So it's the availability of data is driving the program. So if I do y is equal to x plus 10, and x is still unbound, then I cannot do the addition. So this is not an error. The program will just wait. It will just wait. Y is x plus 10, it will just wait. And it will wait forever. There's no timeout or anything like that. It will just wait. And it can wait for a very long time, or forever. Okay? And then, when activity B, it's not 20, it's 1. Binds x equal 1 at point 2. Then, the first one, the addition, it's doing 1 plus 10. It can continue then. Okay? So there's a communication between the two activities. And it's the availability of the data that is what drives the execution. See how it works, huh? When the X becomes available, the activity A will continue. And if activity B runs first, it does X equal 1 before A, that's fine. Then A will just not wait at all. It will just do Y equals 1 plus 10. Okay? So A does not have to wait in that case. Huh? So in both executions, where you first do the addition, if you first do the addition, it will just wait. Okay? And then you do X equal 1. But if you first do X equal 1, then the addition does not have to wait. So you see, the two executions are different, but the result is the same. Y is equal to 11. Okay? And that's very important. That's because it's functional. X is a single assignment variable. When it's bound, it's always bound to the same value. Okay? So this is how the execution works. Notice, so I will fix the slide before I put it in the Moodle. Some bug with the slide, so that's okay. I'll put these slides in the Moodle. So this lets you do concurrent programming. Now this is an easy case. X is just a number. But what if we want to send more values? What if we want to send many values from one thread to the other? Well, then what we share is not a number, but is a list. If the two threads share a list, then one thread is creating the list and the other one is reading it. Then you can send many values. This is very important, and we give it a name. We call this a stream. So a stream is a list which ends with an unbound variable at the end. And if you extend the stream, it's like sending values on a communication channel. Okay? So if I have a stream, let me call it S, which is like a list, 1, 2, 3. But here there will be an unbound variable, S2. And if I read it, 1, 2, 3, then if I try to read S2, I will wait, like the addition waits. Then if I bind S2, like this, then the execution, the reader will continue. So you can see we can have actually producer and consumer. Let me make a diagram here. Producer and consumer with a stream in the middle. 1, 2, 3. So the producer is creating the list. Here's a simple producer, which is doing n bar prod n plus 1. So this is like an infinite loop. If I do prod of 1, it's creating a list that goes forever. 1, 2, 3, it'll keep going forever. It's like an infinite loop. So this is like a producer that is producing numbers forever. And the consumer here is S const, is reading S. It uses case statement. See how it works here? So the case statement has to read the list. But if the S is still unbound, it's just going to wait, like the addition waits, the data flow. See, so this is data flow. Again, it's data flow. And so the consumer will wait until the producer is producing. So the two threads are synchronizing to each other through the data flow. You see how it works, This is really important because this is the foundation for everything we're going to see in this course. And if I take these two functions, prod and const, producer and consumer, and I put them in two threads, and S is a shared variable, but S is a stream, so it's a list, but I'm building it, I'm adding elements. So it's never finished, actually, It's actually keep building it. It's like a communication channel between two agents, okay? So an agent is a concurrent activity that reads and writes streams. So the producer and the consumer are agents here. The producer is creating one stream and the consumer is reading a stream. But they can read and write more than one. And we saw examples of that in the last course. And all list functions can be used as agents. Because they are Taylor recursive, they have constant step size. That means even though you have a loop here, const is Taylor recursive. But even functions like map are Taylor recursive, okay? And that means that the step size is constant. It's really a while loop, okay? And that means if you put it inside a thread, the thread is not going to grow the size. It's going to stay constant size. So it's a really nice concurrent activity. Okay, it's efficient. So it's really important that the list functions are Taylor recursive. Okay, you see that? That's really an important thing. And why are they Taylor recursive? Because of unbound variables. So all of that is pushing declarative programming farther and farther. We make it concurrent now, and it's still functional. But next we will make it lazy, okay? And then we will do advanced algorithm design. We will push even farther the declarative techniques. But this is the first technique, which is what we saw last week, last course, okay? So you understand that, the deterministic data flow, and using a stream lets you send many values, and the data flow is how the two activities are synchronizing between each other. Okay? Okay, so we saw many examples of that, where you have many streams coming in and so on. Okay, so now there's a joker in the deck, which is called nondeterminism, and we saw a little bit of that last course. Nondeterminism is kind of like a demon. Okay, it's something we have to control. It's an evil thing, if you want. So we need to control it. So I want to refresh your memory on nondeterminism. And so I explained a little bit the semantics of concurrency. So technically, what is actually going on when we have concurrent programming? So here we have two threads. Okay? We have two threads, T1 and T2. And each thread is like a sequential program, okay? It's executing sequence. So here we have, I will write it kind of symbolically. E0 is like an execution state. It's there, it's executed, and then it does one instruction, goes to E1, okay? So we saw what it means in the previous course. The execution state is the instructions plus the memory, okay? Together is the execution state. So T1 is like a sequential program, and T2 is another sequential program. So the two threads, semantically, are two sequential programs that are just running, okay, separately. Now that's the semantics, the theory of it, but in fact, they're running on one processor, okay? And a processor is a sequential beast. It executes one instruction sequence. So we're assuming here a single core machine. Now we have computers multi-core, so they're actually parallel machines. And mapping a program onto multiple cores is a whole different ballgame, so I will not, that's a separate issue, okay? The basic idea is you have a single instruction sequence in the hardware, and you can have many threads. I can have hundreds or thousands of threads, and they're all running on one processor. So you have to do that. You have to run all those threads on one processor. So how does that work? Okay, it works because of a technique called interleaving. All of the threads will execute on the one processor, but they will be interleaved. It means that sometimes one thread will execute and then another one, and so on. Okay? And so if you have the processor here, and here's the processor, and it's running, and it's doing instructions. Sometimes it will do an instruction from T1, sometimes it will do an instruction from T2, then it will do again T1, maybe another T1, T2, and so on. So it's interleaving the threads, okay? These threads are running on the same processor. But still, the programmer does not see that. The programmer thinks that the two threads are independent, okay? That means that you have to do this in kind of in the right way. There's kind of some techniques you have to use. Okay, so there's a part of the system called the scheduler, which is deciding at every step which thread to execute. Okay, T1, now T2. So the scheduler is very important. Okay, it has to satisfy certain properties because the threads are independent. So the first property that the scheduler has to satisfy, it has to be fair, fairness. This is fundamental. It means that schedulers cannot be cannot forget a thread, okay? Every thread has to run, okay? every thread has to run. So that means the scheduler has to remember to execute all the threads. That means every thread has to get some percentage of the processor. Okay? So we say the scheduler has to be fair. Okay? That's the main property of the scheduler. Now, real systems, it's not good enough to be fair. Because this is a very fast, this is a very short time. Maybe this is only 0.3 nanoseconds between two instructions, okay? So you can't actually run the scheduler every instruction. That would make your system very slow, because the scheduler is a program that decides things. That means that a real system will use a concept called time slice. That means it will say T1 can run for a long time, like 10 milliseconds, which is a long time. And then you have a hardware interrupt. So you have a hardware clock that interrupts that 10 millisecond, and it brings the control back to the scheduler. And then the scheduler will decide what is the new thread it's executing. Okay? So what that means is that the scheduler only has to run once every 10 milliseconds. So the overhead for the scheduler is very small. But it also means that threads that are not very fine-grained, that means if you have really large number of threads, really thousands of threads, sometimes the thread has to wait a long time before it can run. Okay, so that's something you have to be aware of when you make concurrent programs, okay, with the standard kind of computers. The time slices. The second concept is priorities, because some threads are more important than others. Okay? Some threads are more important. For example, if a packet comes in from the network, that packet has to be stored in memory very fast, because the network connection is very fast and new packets are coming in all the time. So when a packet comes in, the system interrupts its execution and it executes another thread. And this thread is given a high priority. That means it gets a larger percentage of the compute. Okay? And for other reasons, you can have low priorities. For example, a system like Oz or Java, it does garbage collection. It's automatic memory management. But that takes time also. It's a program that's running. And you don't want to interrupt the system. So this kind of an action has a low priority. You will run it when there's nothing else to run. Okay? Then you will do the garbage collection. So the scheduler, it's not just fairness, it also adds time slices and priorities. Okay? So all of the computer systems will do something like that. So that's something you have to be aware of. But the scheduler is a powerful entity, okay? The scheduler has a lot of power because it decides how your program is running. And this is how we get into nondeterminism, okay? So nondeterminism, a program is nondeterministic when it's executing an operation that it's chosen external, outside of the program. That means it's not the program that decides what to execute, somebody else decides. It's not the application developer. In a concurrent system, it's the scheduler who is deciding what to run. So that makes the program non-deterministic. Okay? That means if you run the same program more than once, you can run different operations in different order. Okay? The result might still be the same, though. People sometimes don't understand non-determinism. Okay? It does not mean that the result is always is different. Maybe the result is the same, but the program is still non-deterministic because there's somebody choosing new operations. Okay? So any concurrent program, by definition, is non-deterministic. If it has at least 2 threads, huh? If there's only 1 thread, it's not. It has to have at least 2 threads, huh? Because threads are independent. Independent means that the programmer does not control how the threads are running between them, okay? Which one is faster? They're independent, and that means that when you map them onto the processor, it cannot be the programmer that does it. Otherwise, they would not be independent. You see, concurrency is connected to independence. So the scheduler makes its choice outside of the control of the programmer. Okay? See that? So non-determinism is really an important thing. Non-determinism is the thing we have to control in a program. Okay? So it's inherent to any concurrent programming, but in fact it's stronger than that. Not the real meaning of non-determinism is when your program interacts with the real world. Let's say I run a program, it does computation by itself, it's reading a file, it writes a file. It's a very nice little program. But it's not interacting with the real world. It's not interacting with human beings, it's not controlling an automobile or an airplane or anything. But the real world is a very unpredictable place, okay? When I press a key, it happens anytime. The programmer does not know when I'm pressing that key, okay? It can happen at any time, and I can press any key. So an interaction with the real world is very unpredictable. And when I do that interaction, the programmer has to execute something. So you see, it's non-deterministic. So the real source of non-determinism is interaction with the real world. This is something we're going to see very strong in this course, okay? And concurrency is just a consequence. Why do you want your program to be concurrent? Because you want it to interact with the real world. And if I make many threads, one thread will handle the display or the keyboard. And one thread will handle a user. And one thread will handle another user. So usually when you make threads, it's because you're interacting with the real world. Okay? To interact with the real world, the program must be concurrent. If it's a sequential program, it's very hard to interact with the real world because it already knows what instructions it's executing. What happens when the new instruction, the key is pressed? Well, the program does nothing. Maybe it does polling. Maybe it will check eventually to see whether there's a key pressed. Well, that gives you kind of a delay, okay? It doesn't work very well. So to interact with the real world, the program has to be concurrent. Okay, so we saw some of this last year in the 1104 course, but it was not really very, it's kind of subtle concept. So in this course, we're going to push strongly on this. We're going to see how far can you avoid non-determinism and how far do you need to accept it. This is really the thing that determines how programs run. So many, how do you say, computing programmers of the old style, people who are since 30 years in the industry, this is not so well understood. Okay, this is something that is connected to declarative programming. A declarative program is not non-deterministic; it's deterministic. Okay, so it cannot interact with the real world. Okay, but you want to interact with the real world. So how do you manage that? How do you interact with the real world and you stay declarative? So that's something we're going to see really in this course. And then kind of you will be prepared for the future. Okay? With this knowledge, you will be really prepared to make large programs that interact with the real world. Okay, so we saw an example. Let me refresh your memory on this very simple example we saw. that shows exactly, it's a typical example. There's other examples, you see, but this one is a typical example that shows where non-determinism is coming from. So this is a client server. It's very common. We have many clients, web browsers talking to Amazon, for example. It's a very common thing, client server. And this is a program that is inherently non-deterministic. And the reason is the specification of it. When a client makes a request, the server must respond in a timely fashion. That means not waiting too long. That depends only on the network travel time and the computation time of the request. That's very logical. If I send a message to Amazon, the message takes time to go there, and then it does a computation, has like database, and comes back. So the time should be only that. It should not depend on other clients, okay? So this is, because of this, it's non-deterministic. This specification, by its just that, forces the program to be non-deterministic. Okay? So why is that? Well, let's say you have two clients. Each client is independent because of the specification. It makes a message. It doesn't care about the other one. That means if client 1 sends a message to the server, when that message arrives, the server has to treat it, okay? Or when client 2 sends a message, the server has to treat that message, okay? That means the server has to treat whichever message arrives first. That's a consequence of the specification. You can't say client 1 has priority, so I first handle message client 1, and I will handle message from client 2 only when client 1 sends a message. It doesn't work. Client 2 will have to be handled even if client 1 does nothing. Okay? And on the other side says 2. Okay? So what message is going to arrive first at the server? It'll be either client 1 or client 2. But we don't know which one. It's not determined by the program. It's determined external to the program. Okay? So that point where the server receives messages is non-determinism. It's a point of non-determinism. Okay? So this seems very simple, but it's a massive, it has enormous consequence. It means you cannot write this program in a declarative way because it's fundamentally non-deterministic. Okay? But you can write most of it can be deterministic. The server might be a million lines of code, huge database. That can be completely deterministic. There's only one point, which is right there, which is non-deterministic. It means that most of the program is purely declarative, except for one point where it's not. Okay? This is a very important thing to realize, important insight. It means that most of your code can be declarative, even if your program interacts with the real world. Okay? So the point is, a non-deterministic program is much harder to develop than a deterministic program because it's so many possibilities. It must work correctly for all possible non-deterministic choices. Usually there's a huge number of them. Keys presses can come at millions of possible time instants. There are many, many choices, and they can happen any time. How do you test that? You know, how do you test a non-deterministic program? It's very hard. And almost all of the headaches that people at Google get is from this. And I know for a fact, okay? Because I know many people. And I know, for example, a former student of mine who's working on a big concurrent program. And I read him on Twitter, and he said, "Oh, I spent 10 hours trying to find a non-determinism bug because of a simple thing like this." the guy wasted his whole weekend because of one simple bug, because of non-determinism. Okay, so I'm going to try to keep you, make it so you don't have so many headaches later on. Okay, it's very important. Almost all of the debugging of industry code is this: is problems because of non-determinism. This is not so widely known, huh? But it's true. I know this because I know a huge number of people in industry. So I've been doing this for many years, okay? Lots of gray hair, okay? So, and I know what makes these people cry in their sleep. It's non-determinism, okay? So what can we do? This is what we're going to do in this course. In this course, I want to teach you how to tame non-determinism, okay? See, so it's very important, and you will, 10 years later, or 20 years later, you will come back and thank me, I hope, on that. So, how to live with non-determinism. This is a main theme of the course. So there's two possibilities. Deterministic data flow. Make your program functional, declarative. This first solves the problem completely, okay? Because even though the scheduler is doing non-deterministic choices, the results of the program are always the same for a deterministic data flow. The paradigm is protecting you, okay? The non-determinism is hidden because of the strong properties of functional programming. So functional programming is like a warrior, like Warhammer or whatever. It's a space marine protecting you from non-determinism, okay? Functional programming is protecting you. So that's the preferred way. But you can't always do that. So you want to do it most of the time. So for non-declarative programs, we have to solve the problem. So the real solution is the right abstractions, and the way to do it is to minimize the non-determinism. Try to bring in declarative abstractions as much as possible, okay? So that's what we're going to see in this program. So you see this course is kind of like a crusade a little bit, huh? You see many things, but there's this theme of this course, huh? You get it, huh? Okay, very good, good. So now you know what's going to happen in the course. So concurrency, declarative, non-declarative, okay? And so today I explained kind of the real fundamental goal. So you really know what's going on, huh? Whenever I teach you something, you know the reason, huh? And I refreshed your memory on the previous course today, so I hope you get it now, what we saw in that previous course. And the next week, we will talk about a totally new, different paradigm called lazy evaluation. Very powerful, new declarative paradigm that you have not seen before. We did not see it in the previous course. But it's still declarative, it's still functional, so it's still a warrior, it's still deterministic, okay? So we're giving you more power. We're increasing the power of declarative programming. Okay. Okay, so I think that's good. So I think I will end there. I think I said what I wanted to say today. So you see now what this course is really about. And I will try to make slides. So this course is a new course. Last year it was given for the first time. And for some of the lectures I did not have slides. I will try to make slides for all of the lectures this year. But they may be in the last minute, okay? These slides, I will put them on the Moodle. They're not at the Moodle yet, but I will put them on the Moodle today. So this year you will have slides. So I think that will help, okay? Okay, let me stop there. So I'm a little bit in advance, but that's not a problem. So you get it now, I hope, what it's all about. Okay, so thank you very much.